Time for the fall 2018 final for MA266. We're going through the entire thing. And yeah, nothing else to say. Let's get going. Let's find the explicit solution to this initial value problem here. So, if you take a look here, we have some function of t times 1 over some function of y. So if we multiply that y to our other side, we have y dy dt is equal to 1 over root 1 plus t squared. We can multiply this dt over and integrate both sides and apply our initial condition, and we should be done. Y squared over 2 is equal to this integral. Sorry, this is not a 1 up here, is it? This is a t, which means that we can do a u substitution. U is equal to 1 plus t squared. Du is equal to 2t, and so this integral will become 1 over 2 times 1 over root u, which is u to the negative 1/2 du. So we will get positive u to the 1/2 when we integrate, replacing our u with our original substitution, 1 plus t squared to the 1/2. So we should get, and then plus c. We have our plus c in here. So this is equal to the square root of 1 plus t squared plus c. Multiply everything by 2. We can just have that 2 absorbed into that constant and take our square root, and we'll have an explicit solution there. So since we see that our initial condition leads to a y value of negative 2, we have to be using the negative side of this plus or minus, and using y at 0 is equal to negative 2. Negative 2 is equal to negative square root of, well, the square root of 1 times 2, so 2 plus c. So c must be 2. That leads us to option D. We have a salt tank application problem. Our equation for this will be dq over dt plus r0 over v of t times q is equal to ri ci, where r0 and ri correspond to the rate at which water is entering our tank and the rate at which water is going out of our tank, so that's the O and the I. V of t is the expression for the volume of the tank as a function of time, and Ci is the concentration, in this case of kilograms in units of kilograms per liter of the incoming, actually this is salt, not sugar, whatever. So let's replace all these values and we should be good to go. dq dt plus r0, well, flowing into the tank at a rate of 2 liters per minute, out of the tank at a rate of 5, so 5 liters per minute out. And then a V of t will be 100 initial liters, and every second 2 flow in, 3 flow out, so minus 3t times q is equal to RICI. Rate in is 2, and there's our concentration in, so we have 2 times 2 plus cosine 3t. If we subtract our q term over, we are left with option B. Let's find the implicit solution to this initial value problem. This is looking extremely exact right now. This is about what we would expect the form of an exact equation to be, but in order to check, we have to check if this function, which we'll call m, whether its partial derivative with respect to y is the same as the partial derivative of this guy with respect to x. And in doing so, the partial derivative of, so my will be x, negative xy sine x squared plus y squared over 2. Is that right? I think that should be. Yeah, and then nx will give us negative xy sine x squared plus y squared over 2. So we're getting the same thing, and I hope my differentiation is correct there. Calc 1's hard. And as a result, we can go and solve the integral of m dx and compare that with the integral of n dy, and we'll be able to pull out the function whose partial derivative with respect to x gives us m, and whose partial derivative with respect to y gives us n. I'd also like to point out how nice of an integral that is. Sometimes they turn out that way. So the integral of m dx is the integral of x cosine x squared plus y squared over 2 sorry, not dy, we're doing this dx. We can perform a little u substitution here. U is equal to x squared plus y squared over 2. The du dx is equal to 2x sorry, not 2x dx, just x dx. And so we can rewrite this as the integral of cosine of u du. So we just get negative sine of, sorry, the positive sine of x squared plus y squared over 2. If we take the integral of this portion of n dy, we will also get this term. And then if we integrate this 2y dy, we will get a y squared. So this function right here, and you can check it for yourself, if we take the partial derivative of this with respect to y, as I said, we're going to get our function n up here, and then if we take our partial derivative with respect to x, we will end up with m. And if you want to, this was not a particularly good explanation of actually what's going on behind the scenes with these exact equations. My equaling nx is an important thing. So if that's still confusing for you, I have a whole video for all the exact equation questions. Go watch that. I don't know. I should have done a better job with that. So this is our function here, and in order to set it up as the solution, we need to set it equal to some function c. And given that, sorry, not some function, some constant c, I'm really losing it here. So given that y at 0 is equal to root pi, we can say that the sine of x squared, which is 0 squared plus y squared, is pi over 2, sine of pi over 2, which is 1, plus y squared, which is pi, is equal to c. So pi plus 1, so E is our answer for 3. Let's find the implicit solution to this initial value problem. So when we're seeing y over x's, that's a really good hint that we should perform our substitution. V equals y over x, dv dx is equal, dv dx times x plus v is equal to dy dx. There we go. That said, if you go look at one of the exact equation questions on the 2019 fall exam, there's one that looks almost identical to this, but this substitution does not work. It even has like a y over x and then a rational expression, which you can kind of put into the right form, but it really doesn't work. It turns out that it's an exact equation in disguise, which is extremely weird. So that said, we're going to perform both these substitutions. So our dy dx becomes dv dx times x plus v, and then we get v plus, well, what can we do with this bit? Let's divide everything, the top and the bottom of this rational expression by x. So we get x over x, which is 1, and then 2 times y over x, which is v, plus x over x, which is 1. Looks good. Okay, we can subtract a v from both sides, and now our expression should be separable. Let's multiply a 2v plus 1 over to the left side. We have 2v plus 2 dv, and then let's multiply dx over here and divide 1 over x and integrate both sides. We get v squared plus 2v is equal to ln x plus c. We can undo our substitution and get y squared over x squared plus 2y over x is equal to ln x plus c. Multiplying x squared into everything, and we will get y squared plus 2yx is equal to x squared ln x plus x squared c. We can solve for this c by plugging in y at 1 is equal to 1. So 1 plus 2 is equal to 0 plus c. So c is 3, and that leaves us with option C for 4. Let's approximate y at 3 using Euler's method with a time step h equals 1, where y solves that initial value problem there. So we know that y at 0 is equal to 2, therefore we can approximate y at 1 step size above that, so y at 1. It's approximately equal to what y at 0 was. That's 2 plus our step size 1 multiplied by y prime evaluated at this most recent known condition. So plugging in 0, 2 to this y prime, we get the cosine of 0, which is 1, times 2. So 2 minus 0 is just 2. We get that y at 1 is approximately equal to 4. So now we can approximate y at 2. That will be equal to, or approximately equal to, y at 1, which was approximately 4. And then we're adding our step size of 1 multiplied by y prime evaluated at 1 and 4. So we get the cosine of pi, which is -1 times y, so -4 minus t, so -1. And we get y at 2 is approximately -1. So y at 3 we can approximate as y at 2, -1 plus 1 multiplied by y prime evaluated at 2, -1. That gives us -1 minus 2, so we get -4 as our answer for 5. 6. Let y of t be the solution to this initial value problem. Let's find y at 2. If we divide out t from everything, because the coefficient on y prime will be 1, y prime minus 2 over t times y is equal to t cubed, we can call this term p of t and find rho of t. That's e to the integral of p of t, -2 over t dt. That will give us e to the -2 ln t, or t to the -2 power. So this is integrating factor, by the way, if you didn't catch on with that. We can then write y of t as 1 over rho of t, so t squared times the integral of rho of t times q of t, which is our right-hand side term, so long as the coefficient on y prime is 1, so that's t cubed dt. This will turn into, the integral of t dt, so t squared over 2 plus c, like that. Because we know that y at 1 is equal to 0, 0 is equal to 1 times 1/2 plus c, so c must be -1/2. Finding y at 2 will give us 4 times 2 minus 1/2. That is, 4 over 2, so 3 over 2 times 4 is 6. So 6 is D, which is 6. That's cool. Okay, 7. Let's find the set of unstable equilibrium solutions of this expression here. So one nice thing about how these autonomous equation stability questions work is that if you're looking for unstable or stable solutions, you never really have to check a solution that looks like this. So for y is equal to -2, this guy, I'm pretty sure, you can go check it for yourself. Any solution where we have you know, it in this form, y plus 2, and then the whole thing squared, that will be a semi-stable solution. Because if we diagram it out, let's see, we have y is equal to -2, y is equal to 0, and y is equal to 1 as our points of interest. If we plug in something less than -2, this part of the equation is going to be contributing a positive sign, and the rest of this will be doing whatever it's doing. And then if we move to the other side of -2, none of the signs of these first two will have changed, but this one will also be the same, except that at -2 we'll have a slope of 0. So either we're going to flow up asymptotically to 2 and then away from 2 up to 0, or the other way around. So passing through -2 won't actually change the direction of flow. It'll just act as an asymptote to stop it from getting above that. Okay, so let's actually figure out what our signs are in here. So if we plug in -3, we will have a negative number times a negative number times something that's always a positive number. So there we go. If we plug in -1, we'll have -1 times -2, so two negative numbers times something that's always a positive number. There's that semi-stable behavior I was talking about. If we plug in 0.5, we will have a positive number times a negative number times something that's always a positive number, so there's our negative slope. And then if we plug in 2, we will have positive times positive times positive. So our only unstable equilibrium solution is 1, so 7 is B. 8, let's find the solution to this initial value problem. We're going to be solving the characteristic equation r squared plus r plus 5 over 4 because it's a homogeneous situation over here. Set that equal to 0. And let's do our quadratic formula. So -b, -1 over 2 plus or minus the square root of b squared, 1 minus 4ac, so 1 minus 5. So this will turn into 2i, and then we still have to divide by 2. I like to split up the big over 2a thing. And so we get -1/2 plus or minus I. So we can write our characteristic solution, which is just y of t in this case, as e to the -1/2 t sine t plus e to the -1/2 t cosine t. This is going to be a lot of fun taking all these derivatives, but we can actually reduce our work a lot by doing this. So evaluating y at 0, this whole component will go to 0, and so we can just set 3 equal to e to the 0t, so 1 times, and I forgot this, we have a c1 and a c2, that's what we're actually solving for at this point. Yeah, so this component goes to 0, we're left with 3 is equal to c2 times the cosine of 0, so we know that c2 is equal to 3. Now when we take our derivative, actually we're going to have to take the derivative of the whole thing. That's a shame. Yeah, we'll have to take a derivative of everything. So y prime of t is equal to c1 times e to the -1/2 t cosine t minus 1/2 e to the -1/2 t sine t, although we know this component just goes to 0, we shouldn't have even computed it. And this second half here, we will get plus 3 times the derivative of this expression here. And that portion of the equation will only be left with a cosine in it when we are taking the part of the product rule where we take the derivative of e to the negative 1/2 t. So we will be left with negative 1/2 e to the negative 1/2 t cosine t. And then there is a sine term that we would also compute, but just like this one, it doesn't actually matter because it will just go to 0 and we plug in 0 for t. So now solving this, we are left with y prime at 0 is equal to 1. This is equal to c1 plus negative 3 over 2. So adding this over here, we get 5 over 2. And if c1 is equal to 5 over 2, we can look around here, and d seems to, oh no. Oh, yeah, I should be more careful here. I saw these t over 2's, I saw those, and thought they were these t over 2's that we want in the exponent. Okay, that's dumb. We did get the correct answer, but I've got to be more careful with that. 8 is e. 9. The general solution to this homogeneous differential equation is given here. So these are our two fundamental solutions. We're already expecting at this point in the question to have to do variation of parameters if they're giving us this kind of stuff. And yeah, there we go. Apply the method of variation of parameters to find the solution to this the non-homogeneous differential equation there. So the four things we need for variation of parameters, we need y1 of t. That's just our first fundamental solution. That's x squared. And then we need y2 of t, which is our second one, x squared ln x. We also need f of t, which is this right-hand side, so long as the coefficient on our highest derivative, y double prime, is 1. So we need to divide x squared out from everything. So f of t is really just 5 ln x. Then, what's the fourth thing that we need? Well, we need our Wronskian of our two solutions. That's the determinant of the matrix formed by our two fundamental solutions and their first derivatives. And x squared ln x and 2x ln x plus x. So computing this, we will get 2x cubed ln x plus x cubed minus 2x cubed ln x, which leaves us with x cubed. There we go. So setting up our equations for the variation of parameters, yp of t is equal to negative y1, so negative x squared times the integral of y2 of t, x squared ln x, multiplied by f of t, which is just 5 ln x, all over our Wronskian, which is x cubed, so I will get rid of that. There we go, dx. And then we're adding y2, so x squared ln x times the integral, that's a nice integral too, of y1 x squared times f of t, 5 ln x, over our Wronskian, x cubed dx. And at this point, they do pull a little bit of a fast one with the answers because they're not actually looking for us to compute y particular. What I do every single time going through this exam is exactly that. Actually go compute the answers. That's not what they want though. They want the function of the function of x that we have to multiply by our first fundamental solution to get this first portion of our y particular, and then the function of x we multiply by our second fundamental solution. So here is u1, here is don't want to get that ln x, here's u2. But this is kind of annoying how easy this is. They're looking for u1 prime and u2 prime. So those derivatives will cancel out the integrals that we have there, and we are left with just the integrands as u1 and u2. So we get 5 ln x squared, negative 5 ln x squared over x, and 5 ln x over x. And remember, this negative is here because really we have negative 1 times our first fundamental solution times this thing. And since they're looking for everything that we have to multiply by our first fundamental solution, we have to include that negative in there. So 9 is C. 10. A spring mass system set in motion was determined by this initial value problem. What's the amplitude of the motion? Solving our characteristic equation, r squared plus 49 equals 0, r is equal to plus or minus 7i, we can set up, it's really UC, not Y. UC, that's UU. UC, our characteristic solution, is equal to C1 cosine 7t plus C2 sine 7t. UC prime is equal to negative 7c1 sine 7t plus 7c2 cosine 7t. And evaluating for our initial conditions here, y at 0 is equal to 3. The only term that's not equal to 0 here will be this guy right here. So 3 is equal to c1. And then down here, negative 7 is equal to 7c2. So c2 is equal to negative 1. We're looking for the amplitude of the motion. Since we can write UC as 3 cosine 7t minus 1 sine 7t, we know that the amplitude of this motion will be the square root of the sum of the squares of these two. So that's the amplitude is 3 squared plus 1 squared. So that's root 10. So 10 is A. Let's find the general solution of this differential equation. Pulling out our characteristic equation, we get r to the fourth plus 5r squared minus 36 is equal to 0. If I remember correctly, r squared plus 9, r squared minus 4 will do the trick. So r is equal to plus or minus 3i, and r is equal to plus or minus 2. As a result, we should expect to see a C1 cosine 3t and a C2 sine 3t, which we see here. Yeah, actually only there. We don't need to multiply anything by t because we don't have a multiplicity of 2 associated with those roots. So d is our answer, and it also has the e to the negative 2t and the e to the 2t term that we would also expect. So 11 is D. 12. Which of the following functions is the correct form of a particular solution to this equation? So really this is an undetermined coefficients question. We would like our particular, our guess for our particular solution to be a e to the t plus bt plus c e to the negative t plus d cosine t plus e sine t. And this would be our guess if we didn't have any overlap with any of the solutions to our characteristic equation. So solving that, r to the fourth minus 1 is equal to 0. This has solutions for r equals plus or minus 1, r equals plus or minus I, because I squared gives you negative 1, and that squared gives you 1 minus 1, 0. So works for all of those there. As a result, our yc will have an e to the t term, an e to the negative t term, a cosine t term, and a sine t term. And I'm just being lazy and leaving out all the constants because we don't really need to see all of that. We just need to know what is in our yc. As a result, everything that we have overlapping here, so this e to the t term, this c e to the negative t term, this cosine and this sine all have to be multiplied by t. So t, 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 all multiplied in, and that gives us option E for 12. One solution to this differential equation is x. Another solution is in the form y2 is equal to vx. So we're using reduction of order. Reduction of order says that y2 is equal to y1 times the integral of e to the negative integral of p of x dx all over y1 squared dx. Great. This p of x term is exactly what our p of x term is for, what's it called, integrating factor, where we have to divide out the term multiplied by our highest derivative. We'll have y double prime plus 1 over x squared y prime minus 1 over x cubed. I need to turn my Wi-Fi off, I just realized. 1 over x cubed y is equal to 0. So this is our p of t term, the term on y prime. Taking the negative integral of that will give us 1 over x over there. And then replacing our y1 with x, and then we're squaring it, we'll get x squared in that denominator. We can do a u substitution. U is equal to 1 over x. du is equal to negative 1 over x squared dx. So this will become the integral of e to the u negative e to the u du. So we will get e to the 1 over negative e to the 1 over x, and then we're multiplying this by our y1, which is just x. But all they're looking for is the function v that we have to multiply by x to get another solution. And since another solution can be any linear, well, not really, yeah, linear combination, but more importantly, the fundamental solution can be any constant multiple of the solution that we found here. We can remove that negative sign and still have a perfectly valid fundamental solution. So 13 is E. 14, what is the value of f at 3? We got to take this inverse Laplace transform. So splitting things up, we can rewrite this as 4e to the negative alpha. I'm using alpha instead of s, and factor this into alpha, let's see, alpha plus 3, alpha minus 1. Yeah, that works. Okay, and we got to do some partial fractions on this. We can say that a over alpha plus 3 plus b over alpha minus 1 is equal to 1 over alpha plus 3 alpha minus 1. There we go. Multiplying that denominator up, we get a alpha minus a plus b alpha plus 3b is equal to 1. And so we can say that negative 1a plus 3b is equal to 1, and a plus b is equal to 0. So we'll see that b is equal to 1/4, and a is equal to negative 1/4. Using that to our advantage, we can rewrite this as e to the e to the negative alpha. Factoring this 4 in comes in handy here, and we will have negative 1 over alpha plus 3 plus 1 over alpha minus 1. And this we can take the inverse Laplace transform of very easily, because we know that e to the negative cs multiplied by some function whose not partial derivative, I did that yesterday too, whose inverse Laplace transform we know, that's going to be pretty this is a really bad copy of it. Here we go. This is better. Yeah, here we go. E to the, where is it? Yeah, e to the negative cs times f of s, that's going to be uc of t, multiplied by f of t minus c. So what we should be able to do here is find the inverse Laplace transform pen is not cooperating. Find the inverse Laplace transform of this guy just by writing u1 of t, that's coming from the 1 multiplied by negative alpha up here. And then we're just taking the normal inverse Laplace transforms of everything in here and replacing all of the t's we get with t minus c's, which is t minus 1 in our case. We get negative e to the negative 3 t minus 1 plus e to the t minus 1. And we're evaluating this at f, this f of t function, f of t, we're evaluating this at 3. So f of 3, well, u1 of t, the unit step function, at 1 will be equal to 0 for all values of t less than 1, and will be equal to 1 for all values of t greater than or equal to 1. So when we're evaluating at 3, this guy is just equal to 1, and we will have e to the negative 6 plus e to the, negative e to the negative 6 plus e squared. There we go. So C is our answer for 14. 15. What is the solution to this initial value problem? Well, the Laplace transform of y double prime is equal to alpha squared y subscript alpha minus y at 0 times alpha minus y prime at 0. And the Laplace transform of y prime is just alpha y subscript alpha minus y at 0 alpha. So we can take the Laplace transform of both sides of our equation, knowing that y at 0 is a and y prime at 0 is b. We get alpha squared y alpha minus alpha y at 0, so minus alpha a minus y prime at 0, so minus b plus 4 y alpha is equal to capital G of alpha. Okay, let's add alpha a over here and b, and then we can divide out alpha squared plus 4 to leave us with, let's see, over alpha squared plus 4 over alpha squared plus 4 and over alpha squared plus 4. And this just leaves us with y of alpha on that side. And believe it or not, we are almost ready to go. If we take this little b expression over here and mess with it a bit, multiply by 2 on the top and 1/2 outside of it, now this is in a form that we can deal with, especially if we take this b out. Okay, so the inverse Laplace transform of some function whose inverse Laplace transform we know, and some other function whose inverse Laplace transform we know, we can write that as the convolution, so the integral from 0 to t of the inverse Laplace transform of f of s multiplied, evaluated at t minus tau multiplied by g of tau d tau. So let's see what that means. Since we know that the inverse Laplace transform of g of alpha is just g of t, we can do this. We can say that the inverse Laplace transform of this bit is the integral from 0 to t of, well, what do we have other than g of alpha in here? We have 1/2 sine of 2t. So we can take that as our f of t and evaluate it at t minus tau. We get 1/2 sine of 2t minus tau, and then we are multiplying that by g of tau, which is just g of tau, d tau. And then for these other components, alpha times a over alpha squared plus 4. Since a is just a constant, that will be a cosine 2t, and then here we already said that this was b over 2 sine 2t. And as a result, I'm getting option B for 15. And the answer key agrees. 16. We're finding the function y of t that solves this initial value problem here. You gotta love it when the initial conditions are all 0. So the Laplace transform of both sides will be alpha squared y at alpha plus 2 alpha y at alpha. Not sure why I'm saying y at alpha, y of alpha, whatever. And this is an alpha, not an x. Plus 5 y alpha is equal to the Laplace transform of delta at t minus 7. Well, here's delta at t minus 7. There is its Laplace transform. So e to the negative 7 alpha. So rewriting this, we can multiply by 1 over alpha squared plus 2 alpha plus 5, which is a very, very important thing to know how to deal with. So the magic of 1 over alpha squared plus 2 alpha plus 5, you see I'm just dividing out all the coefficients on here if we factor out a y prime, so we're just left with y prime over here. The magic of this thing is that we can write it as 1 over alpha plus 1 squared plus 2 squared. And more accurately, we want this to be 2 and 1/2. And what's so cool about this? Well, this is if we take the inverse Laplace transform of this, we get e to the negative t sine 2t. And we know that if we're multiplying in the alpha land, we're multiplying something by e to the negative cs, all we do to take the inverse Laplace transform of that is multiply it all by the unit step function at this c value, so u7 of t, and then we replace all of the t's that we would otherwise get for our Laplace transform, our inverse Laplace transform, with t minus that c value, so t minus 7. So essentially, let's take the inverse Laplace transform of this, which will just be 1/2 e to the negative t sine of 2t. And then what are we doing? Now? We are multiplying it all by u7 of t and replacing all of the t's in here with t minus 7's. So we have 2 t minus 7 and minus t plus 7. And that gives us answer choice A, because we are looking for y of t at t greater than 7. And when t is greater than 7, the unit step function here will just evaluate to 1, whereas if it's less than 7, it will evaluate to 0. So 16 is A. 17, oh look at that, I got a little Laplace transform table hiding there. We don't need it though. Let's find the Laplace transform of this function right here. With all of these piecewise things, you have exactly one goal. Your goal is to take the function that you create, which goes by all these rules here, has the correct behavior, take that function and mess with it so that whatever function of t you have, all of your t's are in the form of t minus whatever c your uc of t is multiplied by. I'll show you what I mean. So between 0 and pi, we want our function to be 0. We don't really have to do anything for that. And really this is f of t, not y of t. But then for u pi of t, so that this turns on when t is equal to pi, we can multiply that by t minus 2 pi, and then we can subtract u 2 pi of t multiplied by t minus 2 pi. Okay, so what I'm talking about is every single function here, just like this, has to be in the form where we have u at 2 pi, and we have a function of t where all of our t's have a negative 2 pi attached to them. So we have a problem here. We have u at pi, but then we have t minus 2 pi. So what we can do is rewrite f of t as u pi of t times t minus pi, and then what happened here? Well, a negative pi times u pi of t escaped. So if we add that back in, we would get what we have up here. But this we're fine with taking the Laplace transform of, because it's just some constant times u pi of t. So we'll just use that rule right there. So. We already said that this one was fine, so we can just write it down, minus u at 2 pi of t times t minus 2 pi. Awesome. Taking the Laplace transforms of all of these bits, we know that the Laplace transform of uc of t times some function of t, where all of the t's are actually t minus c's, is just e to the negative cs, so negative pi alpha, multiplied by the Laplace transform of f of t, so not f of t minus pi, but just f of t, which is t, and that is 1 over alpha squared. Then we're subtracting pi times e to the negative pi alpha over alpha. Really, you can think about this formula here. uc of t gives you this as just an extension or a special case of this formula where f of t is 1. Because we know that if we follow that, if f of t is 1, then we will get e to the negative cs times the Laplace transform of 1, which is 1 over s. So that's where our 1 over alpha is coming in over here. And then we're subtracting e to the negative 2 pi alpha over alpha squared yet again, like that. And that should be our answer. They write these extremely weirdly, so it's a little difficult to pick out the answer, but I'm pretty sure, ooh, an ellipse, nice. I'm pretty sure we're looking at A, which we are. Okay, that was kind of a, I didn't really check that enough. Okay, we are out of Laplace land. That's nice. And generally in real exams, once you're done with the Laplace transforms, if you're comfortable with everything system of equation related, you're good. You're fine, because the worst thing that they can throw at you is like some complex eigenvalue or multiple eigenvalue stuff, or maybe 2019 fall used system, what was it? Finding the Laplace transform of a system of second order. Yeah, it was really bad, but whatever. 18, a real 2 by 2 matrix A has this eigenvalue with a corresponding eigenvector. We know that in order to find the general solution, the general real solution, we can just take V1, so 1 and 2i, and multiply it by e to the lambda 1, so 3 lambda 1 t, so we'll get 3t, and then we can split off an e to the 2i t, because otherwise, we would have e to the 3 plus 2i t, but because of the substitution we're about to do, it's easier to split them up like this. This e to the 2i t will become cosine of 2t plus I sine 2t, and then we can form our solution as c1 e to the 3t times the real portion of what we get when we expand all of this out. So we get a real value when cosine is multiplied on top, so cosine 2t, and when I sine is multiplied on the bottom, that gives us negative 2 sine 2t. Then we're adding c2 e to the 3t because it's the same real part of our eigenvalue. And we're looking for the imaginary bits. So we'll get an imaginary bit when sine is multiplied on top. We drop the I and we're left with sine 2t, and then cosine multiplied on the bottom gives us 2 cosine 2t. And if I remember correctly, yeah, that's our answer. They don't try to pull any silly stuff. Sometimes they'll change the sign on C1 or C2 and flip the signs in here. But yeah, cosine negative 2 sine, sine 2 cosine. Okay, so C is our answer for 18. 19. The phase portrait of this system has an origin which acts as what? Well, that's just dependent on the signs and types of our eigenvalues. So solving for our eigenvalues, negative 3 minus lambda times negative 1 minus lambda plus 2 is equal to 0. Lambda squared plus 4 lambda minus, plus 3 plus 2 is plus 5 is equal to 0. Lambda plus lambda. Ooh, wait, this won't have any solutions. So I think we need to do negative b over 2a. So negative 2 plus or minus the square root of b squared, which is 16 minus 20 over 2. So we would get 2i, so I over here. Okay, and as a result, we know that having an imaginary part will contribute kind of spiraling behavior to our solutions, and having a negative value for the real part of our solution will mean that solutions will spiral into our origin. Well, they won't spiral as a result of the real part, they'll spiral because of the imaginary, but overall our solutions are spiraling into the origin as time goes on, so we would call the origin an asymptotically stable spiral point because it's the only stable position in the whole plot where every single other point will move asymptotically towards that same stable position. So you can kind of think of it as like a depression in a trampoline or something, that objects will kind of fall into that stable position as time asymptotically approaches infinity. So 19 is A. 20. This matrix has some eigenvalues with corresponding eigenvectors, and it solves this initial value problem. Okay, so really, I think what they're probably trying to get us to do is to solve, to do something with the fundamental matrix. I think you could definitely go down that path, but I'm not going to. I'm not a real fan of dealing with matrix exponential stuff. It gets a little tedious. So because we know that this has eigenvalues of 1 and negative 1, we know that we can use undetermined coefficients pretty easily because our solutions will have e to the t, and e to the negative t, so we don't have any overlap with these two t's. As a result, we can guess our guess for x particular as a b times e to the 2t, and x particular prime will be 2a 2b e to the 2t. Now, before we plug this in to actually solve for everything, notice that if we plug in x and x prime, we will have an e to the 2t in every single component. So therefore, I'm going to divide those out ahead of time so I don't have to write 6 e to the 2t's. So we'll get 2a, 2b as being equal to 2 minus 1, 3 negative 2, multiplied by ab plus 1 negative 2. So expanding this into two equations, 2a is equal to 2a minus b plus 1, and 2b is equal to 3a minus 2b minus 2. This top equation will just become b equals 1, and so 2 is equal to 3a minus 4, so a is equal to 2. As a result, we should be able to write our entire solution. Note that they want the full x of t, so we're going to need to include our solutions here that we found, and so we'll be able to write x of t as c1 v1. So that's kind of why they're giving us eigenvalues and eigenvectors, to make this bit a little easier. c1 v1 e to the t plus c2 v2, which is 1 3, e to the negative t plus this particular solution that we found, which is 2 1 e to the 2t. So solving for x1 of t, we are going to need to find our values for c1 and c2, which we can use x at 0 is equal to 4, 5 to help out with that. That's c1 times 1, 1 plus C2 times 1, 3 plus 2, 1. We can subtract that 2, 1 and get 2, 4 here, and then set up a little matrix with 1, 1, 1, 3, 2, 4 to solve for C1 and C2, and we'll get 0, 2, 2, so 1, 1, 0, 1. So C1 and C2 are 1 and 1. We can replace that there, and I'm glad I'm almost done because dog barking. We can find x1 of t, which they're calling the upper equation here. So that will be 1 e to the t plus 1 e to the negative t plus 2 e to the 2t, which is answer choice D for 20. Okay, sorry about the dog. See ya.